Hi. So I think everyone did really well on the quiz. I thought I'd just probably not go through it. See the quiz, and then one thing is I solved I should mention. So this thing was just using the shortcut method. It's a lot of calculations, so I ended up putting everything into Excel. Let's see. Quiz 10. So it's easier to do this, like to put everything in an Excel sheet. Just put all your equations in it and just, anyway, this is posted, this sheet, that's the solution to the quiz. But for the next quiz, it's going to be a lot. I think the only way to do it is to do it through an Excel sheet like this. So you set up all your parameters, your input numbers are like yellow here, I guess. I had some kind of color code. And the variables like the temperature and pressure. But your input temperature and pressure, and then anyway, everything is kind of set up here. So then if you make a mistake, you can go back and fix it, a lot easier. I also post in like the equations that I need that are in the boxes, So I think that's kind of the way to go about doing these problems. It makes it a lot easier. And then you can use solver routine right in the same spreadsheet where you have all the numbers. Anyway, so maybe take a look at that if you want, because I think everybody did it by hand. So you're bound to like make mistakes when you do it by hand. So it's probably better to go about that route. Other than that, like basically everyone got above a 90 on this, I think. So maybe 1 or 2 people got 80s, but nobody did poorly on this. So it was a pretty good quiz. It wasn't that easy. I think it seemed like it worked out pretty well somehow. Anyway, so if there's any questions on it, I can go through, but basically, I think it was okay. See the chat thing here. So, all right, so that's that business. Then Wednesday is a reading day. So that kind of puts a monkey wrench into things. So I'd like to finish chapter 10. The part of chapter 10 we need to do is just there's 2 parts that are useful, but there's only 1 part that ends up on quizzes. So it's basically the calculating the K ratio and then doing the bubble point temperature. And then the hardest thing is the adiabatic flash. So I'll probably give a problem like, I think 2017 was 2017. There's a problem where you have to do everything like bubble point, dew point, flash it, and then I'm not sure if they do adiabatic flash. The adiabatic flash is kind of a nightmare, but basically it's similar to last week's calculations for vapor pressure, but using those to get composition for a mixture. So you'll see, I'll go through it today, and then hopefully I can get through most of the chapter today, a little bit tomorrow, and then do the problems. Some of the problems like examples on tomorrow. And then Wednesday's off because it's a reading day, and then just do a quiz on Thursday again. That'll be similar to these quizzes. So basically, I think we can do chapter 10 in kind of 1 day a lecture, basically. It's possible. We can see how it goes, but in order to do that, you kind of skip some stuff at the end, but we don't necessarily need the stuff at the end to proceed to chapter 11. So we'll see how it goes. I mean, maybe that's not doable, but I'll try to do it. Let's see. This, that. Expand that a little bit. So chapter 10 is about multi-components. I don't have that thing up either. Let's see. There. All right. So let's save some paper. So when we had a single component, so you can use Gibbs phase rule. So you have F equals the components minus the phases plus 2. F is the degree of freedom. Right, so we had one component and 2 phases. So we ended up with this thing equal 1 degree of freedom. So we could plot like PV and then have isotherms that come down. So you have the equilibrium and it comes down again, right? And we had ideal gas just like that. P goes with 1 over V. And these are at some temperature T1, T2. Right, so the line, this 1 degree of freedom is like this line. So if you add in another component, you have another degree of freedom. Right, so you can't make this plot anymore. You have to fix the temperature. So you're going to do it some temperature. And then you're going to show like pressure versus composition at some fixed temperature. Right, so this is going to go from 0 to 1. So your extra degree of freedom is this composition that shows up. And then you're not going to have a discrete. So here you could have a vapor liquid mixture. Here you're going to have like at one end, you're going to have the saturation pressure of like component 1. And then at the other end, you're going to have the saturation pressure component 2. And in between, you have this separation to you have a vapor liquid. So pressure is high pressure as a liquid and low pressure as a vapor. You can make the same plot for temperature. Right? And here it's the boiling point. Or they'd go the opposite way of that. So this one would be high, that one would be low. So it'd be like this. You have vapor liquid here, high temperatures, vapor, and liquid. So it flips liquid, vapor, vapor, liquid. If you have pressure or temperature, right? And this is composition here. So here we have, this is a tie line, right? So that's a tie line with the if it's vapor, this is vapor over here, and this is liquid over here, right? The low volume one is liquid, the high volume one is vapor. And then if we had some phase in between, so you'd go up here, then this part represents that one. So you'd have that red circle over the total gap gives you the fraction of liquid. Right, so you go opposite side to the phase you're trying to get. Right, so if this was all the way over at the liquid, saturated liquid point, this would be the entire line that would equal 1. And then if it's at the vapor point, that line would be 0, so it'd be 0 over the total. And so that's the tie line rule works here also. It's the same kind of thing. So you're going to have this kind of tie line, and you have some composition in the middle. So you have a mixed phase of liquid and vapor. The difference here is that the liquid and vapor have different compositions. So the vapor is called YI, and then the liquid is called XI. And the same, there's a tie line here. It's an isothermal, the tie line, or isobaric here. And then you have the vapors YI and XIs here. And then the composition of the phase is given by the tie line, like this would give the amount of the liquid. Right? And this part would give you the amount of the vapor. So it's the opposite side gives you the amount. Right, so we're going to talk about liquid by feed or vapor by feed. So it's for a flash tank, you come in, it's going to flash, it's going to make a liquid and a vapor. So you have the feed, so you're going to have this kind of V by F numbers or parameter you want to get out of the flash. And the composition is going to be given, like the Y compositions are here, the X compositions are here. So this is set up for binary. In other words, you have ethanol and methanol mixed. So you're going to have a fraction of methanol, and then 1 minus that will give you the fraction of ethanol. You can also have multiple components. You can have any number, and then you couldn't do it in a 2D plot like this. Then your components would go up. So you'd have more degrees of freedom. You'd have to do one of these plots for a fixed composition of the other one. So it'd be fixed pressure, and so this is fixed pressure because it's temperature. Then we'd have the other compositions. So things get a little different, right? If you're starting in the liquid phase, so if you start in the liquid phase and then you go up, so you have a T composition diagram. It's at fixed pressure. Kind of looks like that. You have the vapor and the liquid. So if I start in the liquid and then I heat, then I reach this point, the first point where the vapor starts to form. This is VL in the middle. Right, so the first point where the vapor starts to form from the liquid is called a bubble point. And then if you start in the vapor and you cool down, and then the first point where the liquid starts to form is called the dew point. So you don't have one temperature where boiling happens like you do with the single phase. There's like two temperatures and two pressures. So the same thing happens to here. Going from liquid, that would be the bubble pressure, and this would be the dew pressure. Right. So in both cases, you have two values. Here with a single phase, you just have one pressure and one temperature where you get the equilibrium. You can have liquid vapor mixture, but it's going to be at a single temperature and pressure. Here, there's two of each. Right? There's an X temperature for the liquid state and a Y for the vapor. That's kind of how this looks. So it's a little bit different than what we've looked at so far. So, but this is a situation where you have a reaction, you have the thing that reactant, you have the two products, you have to separate the three, then you're going to run into this kind of thing. Right? So this is separations. This is just showing the tie lines for different compositions. Right, so as you raise the temperature, you go up, you reach the bubble point. It's going to make a vapor, this composition B. If you raise the temperature a little bit more, the vapor becomes richer in the B component. And then gradually it becomes the same composition as the input when you get to the dew line, because whatever went in has to come out, so it has to match it there. And at that point, the liquid composition, which doesn't exist, is way over here. It's depleted in B, in A. So it's mostly B. So the compositions of both streams change with the temperature. Both sides, the liquid and the vapor, that in equilibrium, the compositions change as you change the temperature. So you need to do calculations to figure out what the compositions are, what the temperature is, what the pressure is sometimes. So basically, there's kind of categories of calculations you can do. And you have to, from a question, you have to be able to understand what point that you need to get to, like dew point, bubble point. Right, so this is just showing how the tie lines work to get the V by F ratio. So it's if you want to get in a temperature composition diagram, the V by F is going to be this like CD over CE, right? For that composition, that would give you the V by F. Anyway, it's the same tie line rule, lever rule that we had before. It's exactly the same as in the single phase. So as long as you're at isothermal, you can kind of get the compositions. All right, so anyway, these are the different problems that you can do. So first off, all these things involve this thing K, which is called the K ratio, which is Y over X. So if we're at an equilibrium point, so you have the two phases in equilibrium, one is giving you the liquid, so that's X, and one is giving you the vapor, so that's Y. So any component of this mixture, A, B, C, D, E, F, you can have as many as you want, is going to have a K ratio that determines the split at a given temperature and pressure between liquid and vapor, right? How does it split? So in different, if it's more volatile, it'll have more vapor. If it's less volatile, it'll have more liquid. This K ratio is going to depend on the saturation pressure. How volatile is it? Okay, so K is going to be the Y composition over the X composition. Right, it's called the K ratio. So if you, Raoult's law says, it's kind of an ideal law, says that you can just take the saturation pressure. So the Y composition is going to be the saturation pressure divided by the total pressure. Right, so you can calculate the saturation pressure with the temperature. The saturation pressure only depends on temperature. So we have this shortcut method. So we have a bunch of ways to get P sat. We have shortcut, we have Anton, we have Prios, some others. So basically, I think there's 5 ways to get it. I can think of 3 offhand, but basically the shortcut method is one that we're going to use in the examples, and then the Anton equation, the ABC from the back of the book. And then you can also use Prios to get the vapor pressure. So it's like the last quiz, we got vapor pressure. Now we're going to use Raoult's law and then say that so Ki equals Yi over Xi, and then Yi equals P sat over P. Right, then you can say that this Ki, so I can plug in Yi here, so you can say it's P sat over P times Xi. Right, so if I can get P sat, which is a function of temperature, and one of these equations that you pick, and then I know the pressure, and if I know the X, I can get the Y, and inversely, if I know the Y, I can get the X. Right, if I say X equals Yi over K, and then K is going to be P sat over P, or P sat, so K is P sat. Let's see, this is confused. K is P sat over P. Right, so this X doesn't belong here. K is just P sat over P. Because Y, if you plug this in, Y is P sat over P, you'll end up with K is P sat. Y isn't P sat over P. Y is P is X times P sat over P. Right, so Y by X is P sat over P. This is where I ran into trouble. Y is X times P sat over P. That's Raoult's law. Right, and then you can just plug it in to get the K is P sat over P. So if we can calculate P sat with temperature, then we can get K. That's one way to get K. Another way to get K is this de Priester chart. Okay, so these are all, this is all depending on Raoult's law, which is not always right. But de Priester chart is an experimental way to get this. So this is an odd looking chart. It's this thing. Oops, here. Okay, so and if you go to the web page, you can download one that's not blurred. So on the web page, somewhere, chapter 10, so de Priester chart is here, somewhere right here. Right, so you can click that, and this one, even though it's, so you can blow this up, it's not blurred much. Okay, so the way to use this is, you have, it's not like a chart or a plot that you've ever seen before, because there's no axes exactly on this, right? So there's just these squiggly lines that show up. So the way to use it is because this is non-ideal. If it was Raoult's law, this would be a straight line, right? But because these are non-ideal, they're squiggly. And then the numbers are all different on these, right? But the numbers are in some pressure, some kind of unit of, actually it's unitless, right? K is a unitless number. So these are just the K ratios. So you have some pressure. This is in PSI, so you have to divide by 16 point, it's been a while since I used PSI, 16.4, I think, to change this into bar, right? So you have to convert PSI to whatever units you want to use. When you find your pressure, say it's 40 PSI, and your temperature, which is in Fahrenheit, so you have to convert that from C to Fahrenheit, say like 200 Fahrenheit, then just draw a straight line from, like use a ruler, go 40 to 200. And pick your material like ethylene, and then that would have a K ratio of 30, meaning that YI by XI is 30, meaning that ethylene is like a gas. It's only going to have a small amount of liquid in equilibrium if it's at 30 PSI and 200 Fahrenheit. Right. So I mean, from this, you could also get the saturation pressure if you wanted, right? But basically, this just gives you directly the K ratio. This de-Priester chart's another way to get the saturation pressure, or you can just get the K ratio from it. So I think this was one or two homeworks where you should just get familiar with using this chart. It's an easy way to get the numbers. You don't have to do any calculations. You just draw a straight line across and pick out the number. The numbers are crammed in here, so it's a little bit hard to read, but right, so that's one way to do this, these problems for vapor liquid equilibrium. Some of the homework used de-Priester chart. Anyway, so this is the series of things that you do. So if you're coming up, so you can just go through these. So we're going to have temperature and composition, 0 and 1. So binary mixture. So this is like composition of A. And then there's a boiling point of B. There's a boiling point of A. And then there's this kind of behavior, like you have this vapor, liquid, vapor, and liquid. Right. So if you want to come to get the boiling point, you're going to start with a liquid who's going to boil a liquid. You're going to raise the temperature and get to this point, and that's where the boiling point is. Right. So at that point, the vapor that you're making, so you have input like XI or XA and XB, right, and the pressure. And then you're saying like, what is this temperature, for instance? Or you might know the temperature and want to know the pressure. What pressure does that mixture boil at? So the solution to that is that the phase you're making, like you're making a vapor phase, the sum of the y's has to equal 1. And each of the y's, y equals ki times xi, which means this thing means the summation of ki xi equals 1. Right? And the ki's are just a function of temperature, because it's going to be p sat over p, wherever that is. Ki is p sat over p. P sat is temperature, and you know the pressure. So you can get the ki's from one of the equations, like shortcut, Anton, Prius, de-Priester chart. And you can just plug in different temperatures until you get this thing sums to 1. So that's a trial and error. And it's a trial and error procedure. You can do that with solver. If you have an equation, you can do it with solver. 1 second. So these things, it's all going to be like solver routines to do this, mostly, right? So it's going to basically Excel, like you're going to have to put everything into Excel and just do solver routines. Then if you want to find the dew point, it's the opposite. You're coming from a vapor and you want to see the first point where it forms a liquid, right? And that's going to be the sum of x equals 1 to make a liquid. So you have y's, and then you want to get the sum x equal 1 and find the t, or find the p. Right, so you're either going to do pressure or do temperature, and the other one's bubble pressure or bubble temperature. Right, they're kind of the same thing, but so you have to draw the chart and figure out exactly where you are for the given problem that you have. That it can get, so you basically interpreting like which of these is the one you want to use is part of the problem. Right, but once you do that, then you can kind of work out like, all right, sum of x equals 1. So I'm going to have to do y by k. I can get k from the temperature, so I vary the temperature. Y is my input, and I get this sum to equal 1 using solver by changing the temperature. Right, so then I can find the due temperature. And the same thing with the pressure. The k will depend on the pressure because you have this k as p sat over p, and p is changing. Right, so you calculate p sat for your fixed temperature and just vary p. So k is going to be p sat over p, so you just vary p until the k gives you the right sum of x equals 1. Right, so there's a variety of these, but they're basically into these 6 categories. Right. So the other issue is you don't know, you're coming in with a composition that's going to split into a vapor and liquid. So you don't have a vapor going to a liquid, you don't have a liquid going to a vapor, you have something of unknown origin, which is going to be called Z instead of X and Y, ZI, and it's going to go into a flash tank and it's going to make a liquid and a vapor under some other condition, like you have T1, T2. And then these streams are going to come out as a V and an L stream, and this is an F stream. And that kind of problem, which is a flash problem, you need V by F. So the quality of what came out, that's basically Q. Right? And then you also need to know like T, what's the temperature where that happens. And then, so you're kind of coming into this situation where you're just landing at some point here, and then you want to flash it into 2 other things. If you're at some temperature, say the temperature is fixed, and then you want to flash into the vapor and liquid components. Then you want to know like both y and x, and you want to know the separation of the 2. Right? You want to know how they separate. So actually, you're looking for this x and that y, and you're looking for the L by V, the total distance over that gap to the opposite side to get the liquid composition, and this thing over the total distance to get the vapor composition, the V by F. Right, so in this case, you need to use tie line and the parallel thing at the same time. So then you have to solve like 2 things at once, 2 or 3 things at once in solver. So you have 2 constraints, and then you have so one of them is going to be the compositions. You're going to have to follow some kind of rule that the rule in this case is that both the sum of x equals 1 and the sum of y equals 1. And then you need one more rule to figure out what's going on. And that rule can be, I know the temperature, or that rule can be, I know that it's adiabatic, so Q equals 0, sum of Q equals 0. Right, so this can get pretty dicey, right? This can get like involved to do this. That's why it says most difficult, quite difficult. These are more involved. Right, so that's kind of the idea. These things are pretty simple to do. Then this gets to be like you have to write some extensive thing, and you cannot do this by hand. Right, this thing has to be done in Excel. It's too much to do it by hand. I mean, in the old days you would do this by hand, but basically you make a lot of mistakes, and it's really difficult to get this to work out by hand. So you can just use solver to do that routine. So I'm going to go through some examples here, which is kind of the main issue. And then hopefully you can get the feel for how this works. Kind of gone through this stuff. This is just showing that, like, if you use the shortcut method to get the vapor pressure, which again is going to be TR, it has to be bigger than 0.5. And then you can just plug that in to get PI sat, and then get the K ratio just from that equation, where P is the critical pressure for each of the components. So each component's going to have a K ratio. It's like a split factor for going to vapor liquid. It's Y over X. So, and it's going to be written in terms of P sat over P. So we went through all that work of getting P sat so we could use it to get the K ratio for separations in a mixture. So this is a single component saturated pressure. I already kind of went through this. Then the flash. So the flash, I didn't exactly go through this equation, but so the idea is you're going to have you're going to separate into a vapor and a liquid in a flash. So you know that the feed has to equal V plus L, and then you want to get V by F, which is the thing you usually solve for, because that's basically Q equality. And that's going to be 1 minus L by V. Right? So you kind of have that expression. And then if you know the composition, so if you're going into a tank with a composition of like ZA and ZB, or it could be multiple compositions, you're going to come out with YA and YB for the vapor, and the liquid's going to be XA and XB, right? So then you can say that you can do this mix, because if you know V by F, that's the fraction that's vapor. So you can say V by F times YA plus L by F times XA equals ZA. So these are the splits, vapor liquid, and so Y and X times the liquid. And then you can rewrite this and solve for well, you can write this just in terms of L by F is 1 minus V by F, because that's how it works out. That's Z, and then you can rearrange this and solve it. Oh, you can write that Y, so Y equals X times K. So Y, like YA equals XA times KA, and KA again is like P sat A over P. Right. Then if you have, and that's going to depend on just the temperature. So you can get Ka from the temperature, you can get Ya, plug it in here, then everything's in terms of X. You can solve for X from this equation, you get this equation. Right, it's got the K in it, which you can get from the temperature, and it's got the Z. And then you can also solve for this in terms of Y and get the Y in terms of K and Z. Right, and you get this V by F in it. So if you know V by F, then you can solve this thing. Right? If you don't know V by F, then you have two unknowns, or three unknowns. You have X, Y, and V by F. And the K's hopefully you can get. Right? So you have three unknowns and two equations. So you short one equation. So the one equation is this. So you can take those two equations and couple them. So you say, like, you're going to say sum of X has to equal 1, sum of Y has to equal 1, so sum of X minus sum of Y equals 0. Then you make this thing called D. Right? D has to be 0, which is sum of X minus sum of Y, because those both would go to 1. Then you couple that and get this kind of mega equation. So that's one equation. And Z's you know, and K's you know. So you're just getting V by F out of this thing with the temperature. So if you don't know the temperature, then you have to solve this using the some other equation. So you can get, once you get V by F, so you can get V by F from this equation with the knowns. So the input is Z, so you know Z. If you know the temperature, you can get V by F. Then once you get V by F, you can plug it in here. You know Z, you know V by F. If you know temperature, you know K, you can get Y and X. Right, so like I said, it's going to be a lot of equations. The best thing is to plug these into Excel, like get this going that way. So if you don't know the temperature, you can still solve this because you have also energy balance. So this is kind of a mass balance, and you can do an energy balance also. So you know the enthalpy going in has to equal the enthalpy going out plus the Q that you put in. So there's two options. You could say that the Q is 0, so it's adiabatic, or you can say I know the temperature and I can just solve this. Right. So this is the heat balance. So you're going to have the sum of the heat going in minus the sum of the heat going out plus Q is 0. So just an energy balance. And then there can also be a heat of mixing, but usually you're going to say that's 0. It can be an enthalpy of mixing. Things can cool down when you mix them. They can heat up when you mix them. Like if you take fresh water and mix it with salt, let's see, the energy that's exothermic, I guess, heats up. I think if you put salt and water. So there's a delta H of mixing. So different fluids will have a different, like water and ethanol reduces in volume. So I think it releases heat. So it heats up when you mix water and ethanol. Right. So anyway, there can be a delta H of mixing, right? That you need to include in this balance, but basically usually you ignore that. You say it's 0. So it's called an ideal mixture. And then you can get the Q out of this. So you can say Q is 0 and set this thing to 0, or you can calculate what the Q is. What is the heat for the mixing? What's the heat balance on the thing? Or you say, if you know Q 0, you can get the temperature of the output of the thing. So, and again, multi-components is just do the sum with more components on it. So it's multi-components isn't that big of a deal. All right, so I wanted to go through this example, 10.1 and maybe 10.2 today if I can. So this is a 3-component. Right, so it's got following propane, isobutane, and butane. And it's just something, so you can kind of think about it like a 2-component, but so I'm just going to draw a picture of a 2-component, but this is actually 3. Right, so you have this thing, you have temperature, you have composition, right? And then I have the T of A and T of B, the boiling temperature. And then I have some composition, right? This is liquid, this is vapor. And I'm going to do a flash. I'm going to end up at a point here. So this is going to separate into 2 things. Vapor here and a liquid here. And this input part is Z. That's ZA. So that's kind of the picture of what's going on here. Right, except we have 3 components instead of 2, but you can't draw it this way. So here P is fixed. This is the scenario of what's going on. It's inside a distillation column, and you have this overhead. Okay, so you don't know what the state is of the overhead. So you can determine the state of the overhead. So it says vapor, so you would want to find the dew point for the overhead to tell what the state is. Right, so for the dew point, you say sum of X equals, so sum of Z equals 1. If you assume Z is X, it would be sum of Z equals 1. And to find the dew point, it would be X is yi divided by ki. So if you know the temperature, so it gives the temperature here. Schematic, use a shortcut K ratio. Condenser must operate in order to condense the overhead product completely at 8 bar. So it's 0.8. You know the pressure. So P equals 0.8 megapascal. And then you need to find the dew temperature. right? So it's this other plot. So you want to find that T, but you can have the saturated pressures here. So that's the saturated pressure of A, the saturated pressure of B. And it has kind of the same shape to it. Right? And we're doing the same thing. We're starting in the middle, and it's going to separate out into these two. This is liquid and vapor. They flip here, so that's X over here. And this is Y here. And so we're going to make those two from this composition in the middle. And you want to solve for, if you want to find the due temperature, you're going to find the sum of X is 1, so it'd be Yi over Ki. So you're starting, say, with a vapor. So we're saying Y is the dew point. You're saying Y is Z. So say Zi over Ki, which is temperature dependent. The sum of that equals 1. Then you find the temperature where that would work. Right, and Ki is the P sat over P. So you know P is 0.8 megapascal. Then you calculate P sat for a different temperature, and then vary the temperature until you got this thing to be 1, and that would be the due temperature. Right, and then you could tell if this was like a vapor phase, a liquid vapor mixed phase, or a liquid phase. If your actual temperature is below the due temperature, then you're in a mixed phase as long as it's above the boiling temperature. So to get the boiling temperature, you do the same, you do T boiling, kind of the same thing, except you'd calculate sum of Zi times Ki equals 1 to get the Y. So the first point of vapor shows up. And you'd vary Ki's P sat over P. P sat depends on temperature. So you'd vary the temperature until that's summed to 1. Then you know the boiling temperature. And if your temperature is between the dew and the boiling, then you know you're in this liquid vapor region, and then you can do this problem, because this problem's about a flash condition. Right, so it's in the liquid vapor region though. I mean, he kind of gives that to you. You could do these calculations for dew and boiling. But he basically in this problem says like he's already there. He's already in that two-phase region. So the first question is using shortcut K ratio, calculate the temperature at which the condenser must operate in order to condense the overhead product completely at 8 bar. So in this case, the product is vapor, right? He wants a vapor thing. It's going to just condense. So he wants to know, so if you're here, and you're in the pressure and you want to condense, so you're coming in with a vapor. So you're here in the vapor. And then you want to condense totally. So you actually have to get to this pressure, to this, let's see, like the temperature, sorry, it's at constant fixed, so 0.8 megapascal. And you're coming in with a vapor, so you're coming down here and you want to know where it totally condenses to this liquid, right? So that's going to be the same composition as what you came in with, this Ci, right? But it's got to be just at the point where it's totally liquid, which is the bubble point. So in order to do this, you have to say, what is T bubble? Right? What's the bubble temperature? Right? The boiling temperature. So basically that's going to come from this kind of balance, right? Zi, some Zi, Ki gives you Yi has to equal 1. When you're coming up from the bottom, it's making a vapor. The vapor has to equal 1. So sum of Yi equals 1. So you're going to have to do this problem, like Zi, Ki, and Ki you get from P sat over P. P sat's temperature dependent. So you need that shortcut method for P sat. You know your P is 0.8 megapascal. You're going to put that in here. And the Z's you're given. They're in the table up here. And you got to iterate that until this thing sums to 1. And that gives you this bubble temperature. And that's the temperature where it'll totally condense to a liquid. It's complicated. But anyway, to do this, so you're gonna have to do some problems on this to figure out how to do it. So you can do this in Excel, right? Like here's an Excel for this guy. It's like he's running slow. Okay, so here's our, so this is a flash. So we're gonna have to use this equation, this flash equation for this. Let's see. For A, we don't need the flash equation. For A, we need the bubble equation. Here, I put these into this is online. Like you can get these Excel sheets online if you want to look at them. Right. So this will increase there. All right. So we want to get. We're making it. We're boiling. We want to get the first point where it'll turn to liquids. That's the first point where it starts to boil. So that's the sum of y equals 1. That's ki xi. So we have, this is K here, K, so there's 3 components, propane, isobutane, and butane, right? So I have the Ks for those here. Those are going to be done with the shortcut method, which is here. So that's going to use PCTC omega. So that's the shortcut method, 10 to the 7/3, whatever, blah, blah, blah. Then divided by F14 is P, the pressure 0.08, which is fixed. Okay, so that gives me this Ki is Pi. That's this equation. Right, so I have calculated, and that depends on TR, which is F5, which is T, wherever T is. T's down here. F13 is T. So it's a TC divided by T to get TR, or it's 1 over that. So it's 1 over TR, so it's TC over T. Right, so those are all the Ks. So they're calculated here, and then you're going to use the Ks in this equation. K times X sum equals 1. Some places the sum has to equal 1. Here, right here. The sum equals 1. So this is K. These are the X's. So Z is a X in this case, and you want it to equal 1. So Z, even though it's coming in as a vapor, you want to totally condense it. So you're going to form, so you're going to form a liquid. So you come in at a vapor, Z, you're going to come in a vapor, you want to form a total liquid, but you're trying to calculate this temperature and the composition of that temperature. So when this first shows up, it's over like this. As the temperature goes down, it goes like that. Then as it goes, it'll eventually be like that. So you have your vapor phase, which is pour in A, and then the liquid phase is exactly what Z is. Right, so the composition, so you take the Z to be X here, so you can get that point. It's confusing, but basically Z can be either Y or X depending on what problem you're looking at. Okay, so in this case, because you're trying to boil to get the bubble point, you need to make Z the input, which is actually a vapor, into the liquid. Because you're going to make pure liquid out of what comes in. You can only do that at the bubble point, right? So that's why you're using Z here to do this sum, and then you just use solver. Then you just use a solver routine to you just do solver to solve the thing. It's using that's your thing. It has to equal 1, and you're going to vary the temperature. And you find that it's 317.6. Right, so that's the standard thing we've been doing. The other parts, that's a bubble point calculation. So anyway, the other parts are I'll have to go through the other parts tomorrow. Right, so I'll start this over and go through this thing tomorrow. So I'll have to quit here. It's 3:20. Oh no, I have a couple minutes, right? Yeah, I get till 3:25, so I can do the next one. When I do that, hold on, don't quit. The next part is the next part. See, I have time. I can do the next one. Use this shortcut K ratio and assume the overhead product vapors are in equilibrium with a liquid on the top plate of the column. Okay, so the vapor is in equilibrium with the liquid. Calculate the temperature of the overhead vapors and the composition of the liquid. Okay, so in this case, you have the vapors in equilibrium with the liquid. So this composition of the vapor has to be just at the dew point for the liquid, right? So you're saying that you have the vapor, then you're right at the dew point, so they're equilibrium. You want to find out the composition X of that liquid, so it has to be like over here. It has to be that X. So you want to find out what is that temperature to be in equilibrium with a liquid, just in equilibrium with it. Right, so you need to find the dew point. So you're taking a vapor and trying to make a liquid with it. So that happens when the sum of X equals 1, and X is 1 is Y divided by K. But K is Y over X, Ki is Y over Xi. So X is going to be Y divided by K. So the sum of Y divided by K, and K is P sat, which depends on temperature, divided by P. Right, so in order to get this, you have to vary this temperature until you get that sum to be 1, and then Y in this case is Zi. So again, like depending on what the problem is, Z can be X or Z can be Y. So it gets kind of confusing. Z is Y, Z is a vapor coming in, but basically you can treat it as a liquid if you're going to totally condense, or you can treat it as the vapor if you're trying to just get the dew point. Right, so that's what this does in the B part of this. So in part B, it's kind of the same thing. In fact, you could copy the other table and just, so you're doing the same calculation using the shortcut method to get the K ratios, and then you're going to then you're calling Y, so Y is Z, so you're doing Z divided by K in this case, and sum those. So F's are the K's and D's are the Z's going in. You sum those to get 1. You're going to do that by varying the temperature. Right? The temperature is here. So you're going to basically, and so the temperature is used to get K, and then you're going to sum that to get 1. So there's a solver routine to do that. It's just like make that 1 by changing the temperature. Right. So these are kind of simple. I mean, they're harder than getting the pressure, but basically it's just a simple solver routine, and you have to set this Excel sheet up properly, right, to get that temperature. So depending on what the problem is, the last one is a flash problem where you're coming in, you don't know the composition, you're going to make the 2, and you need to solve for X and Y at the same time. And so I'll do that one next time, because that one's the hardest one and the most confusing. If this wasn't confusing enough, this one is really confusing. But basically, in this case, you need to also calculate Q. So you can do that in the spreadsheet. It gets to be a little bit more involved. Part C is like got a Q part, and you simultaneously solve it in Excel. So, we're going to use so the solver routine will have 2 constraints on it. That's if it's an adiabatic. This one's not adiabatic. He gives the temperature. This one's just a normal solver. There's an adiabatic one after this. So we'll do flash tanks. I'll do examples of the flash tank next time. And the quiz will be like this, and like this whole thing that I did as far as examples. Like the rest of the chapter we'll use later on, more or less. But basically, this part you have to get is how to do a bubble point, how to do a dew point, and how to do a flash, and an adiabatic flash and isothermal flash. And get the heat from the isothermal and the heat 0 for the adiabatic. So solve for the temperature in the adiabatic. So that's the most important part of the chapter. The rest of it, there's a lot of other parts to the chapter. So it's a long chapter, but basically this is the part that'll be on the quiz. So I think we can get through this today and tomorrow. Hopefully it'll be enough to do the quiz, and we can kind of move on. The reading day, I don't know, it's kind of worthless in the middle of the semester like that. And if you have any suggestions on a reading day, like it doesn't seem like it's much of a break. It's a 1-day thing. I don't know what to tell you. It's just makes it harder to get through the chapter. But anyway, so I'll see you guys tomorrow. Thanks for sticking around. And quit there.